Welcome to This Explainer. Okay, so today we're tackling the absolute bedrock of modern connectivity. I mean, if you've ever stopped and wondered how data literally travels from the device you're on right now, zips across the globe, and lands perfectly on another device, well, it all comes down to an epic tag team dynamic between two essential pieces of hardware, the switch and the router. These two are basically the undisputed masters of the network. Understanding how they operate, how they differ, and honestly, how they collaborate is absolutely crucial for grasping network engineering. Okay, let's dive right into this agenda. First, we'll meet the network masters. Then, we'll look at layer 2 and the switch. After that, layer 3 and the router. Then we'll put them head to head with switch versus router, and finally wrap up with the 3-layer model. So, section 1, meet the network masters. All right, before we separate the switch from the router, we really need to understand the ecosystem they both share. Because while the hardware itself performs very different physical tasks, they are usually driven by the exact same brains, Cisco IOS, or the Internetwork Operating System. This is a multitasking OS, complete with a command line interface, that you're going to find running on the vast majority of Cisco switches and routers. It's the unified platform we use to configure routing, switching, the whole shebang. Oh, and for those of you who might have dealt with older hardware, you might remember that previous versions of Cisco switches ran Cat OS, a legacy system. But today, iOS is the standard you'll be interacting with to give these devices their marching orders. So, to actually get in and configure these devices, network engineers rely on 3 main access methods. First up is console access. This is a direct physical connection using a rollover cable. You'll use this a lot for brand new, out-of-the-box devices that don't even have an IP address yet. Then we have our remote options, Telnet and SSH. But here's a massive, crucial detail you've got to remember. Telnet uses TCP port 23, but it sends all your data, and I mean literally everything, including your admin passwords, in plain, clear text. Because of that huge security flaw, it is basically never used today. Instead, you'll definitely want to use SSH on TCP port 22. That adds a vital layer of security by encrypting all your communications using public key cryptography. It's a real game changer for network security. Moving on to section 2, layer 2, the switch. Now that we know how to log in, let's transition into the local realm of the network. We're zooming right in on layer 2 of the OSI model, the data link layer, where the switch totally reigns supreme. Now, as you probably already know, to understand how a switch works, you have to look at how it identifies devices. It does this using a MAC address. A MAC address is a permanent physical identifier stamped right onto a network interface card. It's 48 bits long, expressed as 12 hexadecimal digits, and it's split perfectly down the middle. The first half is a 6-digit vendor OUI code, which basically just identifies the manufacturer, right? And the second half is a 6-digit vendor-assigned value that is completely unique to that specific piece of hardware. The big takeaway here is that a Layer 2 Ethernet switch makes its forwarding decisions based entirely on these Layer 2 MAC addresses. It totally ignores IP addresses, it doesn't care about the data protocol inside the frame, it only looks at that physical hexadecimal MAC address. Now, what's really fascinating here is how the switch dynamically uses those MAC addresses. It essentially builds what we call a MAC address table, or sometimes you'll hear it called a CAM table. It does this by closely examining the source MAC address of every single frame that enters its ports. Think of it like this. When you power on a brand new switch, that table is completely empty, blank slate. But as devices start chattering, the switch is listening and learning. If a PC sends a frame into port 1, the switch immediately records that PC's MAC address and maps it right to port 1 in its memory. It even uses a refresh timer. By default, most of these Ethernet switches keep an entry in their table for about 5 minutes. This dynamic, self-building table is what allows the switch to efficiently forward frames only to the specific port where the destination device actually lives, instead of clogging up the entire local network. But wait, what happens if a switch gets a frame meant for a MAC address that it just hasn't learned yet? Well, it steps up as the local traffic cop and executes something called an unknown unicast. Basically, if the destination MAC isn't in that table yet, the switch floods the frame out of every single port except the one it just came in on. It's essentially shouting to the whole network, hey, who has this address? Once the correct device hears that and replies, the switch immediately learns its location, slaps it into the MAC address table, and boom, all future traffic is forwarded perfectly without the shouting. All right, section 3, layer 3, the router. So let's zoom out to the macro level now. If the switch handles the local traffic, staying within the same neighborhood, the router is responsible for global navigation. It's taking you between completely different cities. And this brings us right to layer 3 of the OSI model, the network layer.
While switches are obsessed with those physical MAC addresses, routers are all about IP addresses. An IP address is a 32-bit logical address assigned to our devices. Because it's a logical construct rather than a hard-coded physical one, it operates at layer 3. This specific addressing scheme is exactly what allows us to identify and locate any device across entirely different networks all over the world. Literally, without the IP address and the routing protocols that rely on it, the internet as we know it simply would not exist. To pull this off, routers forward IP packets by checking their routing tables. And there are a few different ways these tables get filled up. First, you can use static routes. This is where an admin goes in and manually types the route into the router. It's fantastic for security, and it uses basically zero router CPU overhead. But let's be real, manually updating static routes in a massive enterprise network would literally be a full-time job. It just doesn't scale. So that's where default routes come in to save the day. Routers naturally look for the longest match of a destination IP in their table. If they look and no match is found, they fall back on a default route, which is often configured as all zeros, 0.0.0.0. This acts as a crucial safety net. It sends that unknown packet to a next hop gateway so you don't accidentally create these data black holes where packets are just dropped into the void.
Okay, section 4, switch versus router. We've looked at them individually, sure, but bringing these two devices head-to-head for a direct comparison is really the cornerstone of this whole explainer. So here is the absolute crucial point you need to take away. Layer 2 switches are responsible for switching. They operate at layer 2, they use MAC addresses, and their job is connecting devices within the exact same network. Routers, on the other hand, are responsible for routing. They operate at layer 3, they use IP addresses, and their job is connecting devices between completely different networks. Now, a massive, massive differentiator here is how they handle broadcasts. When a broadcast message hits a switch, the switch just forwards it out over all its ports. But a router stops broadcasts dead in their tracks. It simply will not forward them. And that feature is vital for breaking up huge, noisy networks into smaller, much more manageable broadcast domains. And that fundamental difference in how they handle data brings us to a major performance reality. In fact, let me just highlight this direct quote from the source material. Layer 2 switches are faster than routers because the process of switching is faster than routing. It really is that simple. Because a layer 2 switch doesn't have any IP routing capability, it requires incredibly minimal processing. It just glances at that hardware MAC address and instantly forwards the frame. Routers, meanwhile, have to deeply inspect those layer 3 packets, calculate routes, make complex path determinations, and all of that inherently takes just a fraction more time. Finally, section 5, the 3-layer noddle. And this brilliantly illustrates how these distinct devices don't just exist in a vacuum, right? They unite to form a complete, highly efficient network architecture. Cisco actually defines this through a very specific hierarchical model. Let's just step through this from the bottom up. At the very base, we have the access layer. This is where your everyday layer 2 switches live, providing that direct connectivity and port security for your workstations and servers. Moving up, we hit the distribution layer. This acts as the sort of communication bridge between the access layer and the rest of the network, utilizing routers and multi-layer switches to provide routing, filtering, and WAN access. And finally, at the very top is the core layer. This is the network backbone. It relies on super high-end routers and switches with redundant links to transport massive amounts of traffic as quickly as humanly possible. In this model, every device knows its specific role and its specific layer. But, as technology rapidly evolves, those rigid lines are starting to blur. We now have layer 3 switches, also known as multi-layer switches, sitting right there in the distribution layer that can route IP packets just like a router, all while maintaining the incredibly high speeds of a switch. Which leaves us with a pretty provocative thought to end our explainer today. As these layer 3 switches become more powerful, more affordable, and more ubiquitous, will traditional dedicated layer 3 routers eventually become obsolete in modern corporate networks? It is a fascinating evolution to watch. Thank you so much for joining me for this explainer, and keep questioning how your data flows.